Right, now we are beginning the next chapter. This is about the set systems with restricted intersections. So we're going to spend a few weeks about several topics in this area. So we are interested in the set systems. So it's a collection of sets, a set of sets, such that the intersections between members have certain types. Sometimes union, but intersections, right? So we say a set system F is intersecting if X is intersection Y is non-empty for all X, for all X, Y in F. So what are the examples? Well, I might have subsets containing particular elements, right? So if you want to have a set system over 1 up to n, what is intersecting? What are the examples? So for instance, here's a subset containing 1, right? Then there are 2 to the n minus 1 such sets. So this is an example where there exists intersecting set system over an n element set, and its size is 2 to the n minus 1. Now we're gonna show that actually this is best possible. It's an easy theorem, so let me just state it. If F is an intersecting family of subsets of an n element set S, then size of F is at most 2 to the n minus 1. Maybe it took longer time to actually write down the theorem than figure out the proof. Why? Because there's a pair, right? Yeah, suppose it's bigger than that, then F contains a pair X and Y where Y is equal to S minus X. The Y is the complement of X, right? Among all 2 to the n subsets, you have just pairs, right? Pairs of complements. And since we are taking more than 2 to the n minus 1 subsets, there must exist a pair where both of them are inside F and they're complement to each other. But then X intersection Y is empty. This is not the Erdős-Ko-Rado theorem, so it's easy observation on intersecting family. So Erdős-Ko-Rado theorem is about the uniform family. Okay. So now let F be a K-uniform family of subsets of an n element set S. Okay, I don't have to say S. Then size of S, F is bounded by something. So first of all, I should tell you why I chose K to be n most n over 2. This is because if K is bigger than n over 2, then any two subsets of size K will intersect. So the answer will become n choose K. Oh, I didn't say intersecting. Okay. I should have said that. Right. So if k is bigger than n over 2, then any two subsets of size k will have to have a non-empty intersection, so this family is intersecting. So n choose k is the correct answer. But if k is, so the problem is not interesting. But the only interesting range of k is when k is up to n over 2. And here's the example. Like, how do we build such an example? Well, just make everybody contain 1, right? Like before, right? So since I chose 1 already, so the number of remaining elements is n minus 1, and I chose k minus 1 elements from outside and make a union with 1. So that's the bound that we expect, right? And this bound is tight if true, right? Because we have example. And the original proof by Erdős-Ko-Rado is not as pretty as the proof that I'm going to show you now. This proof is due to Katona, Katona, in 1972. So let's say A1, A2, AM. These are the members of this family. All right. So now I'm thinking of the circle. So for I in 1 up to M, let Pi be the set of all cyclic permutations Oh, by the way, I'm assuming that the ground set is 1 up to n. All cyclic permutations such that all elements of AI occur consecutively in the cyclic order, right? So in other words, I have a round table and I want to put the numbers 1 up to n around the round table, and I'm counting such permutations. So by rotating the table, you have the same permutation, so we should identify them. And Pi is the number of permutations, number of cyclic permutations where all the elements of AI occurs consecutively. So for instance, AI is here. So how many such permutations do we have? Well, size of AI is k, so I first need to take a k factorial ways of putting elements of AI over here, and there are n minus k factorial ways of putting the outsiders, right? So this is the size of Pi. Wait, what about the rotations? Well, it doesn't matter, right? Because when you rotate, it's the same permutation, so I'm not counting that. All right, now let's observe the following. AI intersection AJ is non-empty because it's intersecting. So that means what does that mean? Right. All right. Let me say this way. If I look at the, so number of cyclic permutations, number of all cyclic permutation is, probably you remember this, n minus 1 factorial, because I fix one person, one number in one place, and then remaining n minus 1 people, I take any permutation and put them, right? So that's n minus 1 factorial. Now, for each cyclic permutations, right? Now, this is the key observation. Each cyclic permutation can occur in at most k of p1, p2, pm. Why? Right? Imagine that I have one cyclic permutation. Now it's in AI. Suppose it's in AI. I mean, it's in PI. So that means AI occurs consecutively. And if it's in PJ, then AJ occurs consecutively. But AI intersection AJ is non-empty. Right? So how is it possible? Well, they have to intersect. Right? So the starting place for AJ should be like somewhere near here so that it can intersect. So among all AIs that contains this cyclic permutation, choose the one that occurs in the leftmost, or I mean it's not left, but counterclockwise leftmost. Okay, then the starting place for AJ should be one of these members, right? So that's why you can have at most k of other k indices where PJ contains this particular cyclic permutations. So that means if I add all these numbers from 1 up to m, then that's going to be k times number of cyclic permutations. I mean, that's a maximum number, right? Each cyclic permutation can occur at most k times. So that's k times n minus 1 factorial. So m times k factorial times n minus k factorial is less than or equal to k times n minus 1 factorial. So m is less than or equal to 1 over k minus 1 factorial and n minus k factorial times n minus 1 factorial, which is equal to n minus 1 choose k minus 1. Okay, so that's the brilliant proof. There are many other proofs, but this is the shortest proof. And you use the property, I mean the like counting in a clever way, right? So that's the Erdős-Ko-Rado theorem, and we will continue about on the other types of intersection theorems.